topic of this lecture for today is really just going to be specific to this technique called inverse adding doubling. And it's something where it's probably one of the simplest approaches, at least calculation-wise, in terms of taking measured data and determining what the optical properties are that derive that measurement. So again, this is this idea of having an inverse solver versus a forward model for light transport. So the teaching objectives for this lecture is basically to understand what this adding doubling method is, the fact that it is an exact solution of the radius of transport equation. However, the only reason why it's exact, it's under extremely simplified boundary conditions. So again, this is a technique that can be used to describe slabs of tissue. But also then, how can we use these solutions of the adding doubling models, so this forward model, to experimentally to actually get the opposite, so this inverse adding doubling approach. And again, the basis for this is a forward model will describe light in terms of the total reflectance or transmittance or light transport through tissue. What we're looking at now is taking a measurement of that end result, the output of that, and trying to put it back in to get what were the parameters involved in generating these results. So it uses these solutions of adding doubling and then infer the optical properties within this homogeneous slab of tissue. And then the last objective is to actually get some appreciation of what does it actually take to use adding doubling as an inverse solver. And so again, the measurement, the experimental part is you measure total reflectance and transmittance of a thin tissue and try to use that end result and minimize back to what would be the parameters that would actually run this model to generate those results. So the outline for this talk, again, I'm going to try to reintroduce this concept of an inverse solver method, and then go into the forward model of this adding doubling and go through the principles of its operation. Then goes to say, now that we understand how this model will describe light transport under these very limited conditions, how do we then go through and do the inverse? And not just think about it in terms of these idealized measurements, but then to also go into considerations of physical measurements. So what kind of instrumentation would it take? What kind of calibration do you need to actually get back to this idealized case? And some considerations on sample geometry and constraints. What would be the range of samples that you could actually measure with this? And then some strategies for actually managing the experimental conditions. Then leaves with some take-home messages, and if time permits, go through some examples of how we've actually used this technique here at BLI to do some basic research. And then any discussion in conclusion there. So, introduction to inverse solvers. So again, concepts that were brought up on the first day and probably yesterday and even maybe in Boston's talk this morning. So the forward model, it's something that describes what happens to light in the media as a function of the properties of that media. So typically, for the majority of the lectures here, these properties of media that we are interested in are mu sub A, mu sub S, so absorption, scattering, the anisotropy, index of refraction, and there could be other more subtle things, but primarily a lot of these techniques are geared towards diffuse reflectance, describing it in terms of scattering and absorption. And then these forward models will generate outputs, which again, things like radiance, fluence, so a way of describing an output in terms of what's within the media volume or what's at the boundaries. But in contrast, now the inverse model infers the properties of the tissue on measurable outputs of an unknown medium. So again, your tissue is considered a black box. You measure something from it. And the issue there is usually the measurable outputs, the things that you can measure, are not sufficient to describe all the different optical properties within the tissue. So, there's usually ways that we can try to constrain it, assume that media is homogeneous, assume that you know what the index of refraction is, and in some cases, that you know what the anisotropy is. So there you can have, say, two measurements, solve for two unknowns, but again, that's all very assumption heavy. But again, given your problem through a careful selection of a forward model, assumptions of the tissue properties and distribution, placing constraints on the measurement geometry, and other experimental conditions. So again, rather than looking at a steady state solution, doing some kind of perturbation, you can tease out this additional information. Inverse solutions are achievable. So again, it's just a consequence of really understanding what the problem is, what the strengths and weaknesses are, and how do you then go through and say, do I have sufficient measurement to describe the properties of the tissue I'm looking for or not? So there are a variety of models and methods that have been developed to date. Again, was brought up the delta P1 model, standard diffusion, Monte Carlo, and again, they all have their own respective strengths and weaknesses, though apparently delta P1 has no weakness. But typically you can describe this in terms of computational burden versus accuracy. So things that will be much more computationally intensive tend to have more accurate results, but again, will take a long time for it to actually come up with an inverse solution. There's also measurement complexity versus acquisition time. So you can have more detailed measurements, a higher number of different types of measurements, but that will lend to the complexity of the system, giving you maybe more information, but it will take a longer time. It might be more expensive to do that type of measurement versus a quick measurement. Sensitivity to spatial heterogeneity. So again, a lot of the models, especially with standard diffusion, you have this basic assumption that everything's homogeneous. And so if it isn't, you're going to have some deviation, some error in that result. Certain techniques are more adaptive to it than others. And of course, from a practical standpoint, instrumentation cost. So, if you have several $1 million, you can build a wonderful instrument, but how good is it if you can't take it anywhere? So, there's a leverage between how much you want to spend versus, what do you really want to get out of it. So, just as a general theme, so in my mind, the key to successful research is to understand when and or where each method would best address the problem that you wish to attack. So again, an awareness of what's out there will help you narrow down to say, if this is what I'm looking at, these are the challenges with the particular clinical problem that I'm looking at. What are my options? What do I give up going with one approach versus another? And that kind of informed approach will give you the best opportunity for success. So that was just kind of a general pretext. So now let's go into what the adding doubling method really is. So again, it's a forward model. It's a model that describes radiance. So again, this is the measurable quantity at boundaries of tissue. And in general, radiance is described in terms of position, angle, and time. So it's this 6-dimensional property. But the key thing that adding doubling does and allows it to actually have an exact solution of the radiative transport equation is the fact that we take all this and simplify it down to just a one-dimensional problem. So again, here, huge assumptions on the tissue geometry that we're measuring, but just to kind of give you a taste of what happens is the fact that if we were just to take this down to a single spatial dimension, radiative transport breaks down to just this first-order differential equation coupled equation solution. So again, very much simplified. Our little arguments here are now based on absorption and reduced scattering. So, this is a nice, clean solution, but under very simplified conditions. So, giving you a kind of example of what the result is, I just wanted to go back to the radiative transport equation and just try to convince you that this is an exact solution. So when we're looking at this reduction of dimensionality, so this is our little friend here of the radiative transport equation. So when we reduce the dimensionality, the first thing that we do is we assume that our source is steady state and that our slab of tissue that we're investigating doesn't change with time. So by doing this, we can eliminate all the temporal dependence from the equation, simplifying it down to here. Then we reduce all the spatial components just to one dimension. So light in this case either goes forwards or backwards. So now we have something that's dependent on x. We assume that it's a planar illumination geometry and that if everything's homogeneous, it's an easy assumption to make. And then last is what we do is we integrate over all the angles. So when we are measuring the total reflectance and transmittance, in reality, light can exit that boundary over any angle. But what we're saying here is that we will have a measurement that will just collect all the light over all angles on either side of the slab. And then by integrating over all angles, we have this simplified first order differential equation for radiance in the forward direction and radiance in the backwards direction. And again, radiance in the forward direction, that would be considered what we'll call transmittance, light that goes through the sample. And the radiance in the backwards direction, that's what we will refer to as diffuse reflectance. So light that enters, scatters around, but comes back out in the backward going direction. So first order differential equation, that's why we get that exponential solution that I showed previously. And now let's just try to take a look at this in terms of these radiance in the forward, radiance in the backwards direction. So again, you have these kind of coupled equations here. So the idea is that light going forward at your first boundary, that's your light source. So that's the photons coming in. And then light in the forward direction at your next boundary, that's the transmittance coming back out. You can also potentially have light sources from the other side going backwards, and light going backwards at the first boundary, that's your reflectance. So what you can start to do is actually build up to say, if I can determine what this quantity is here, you would have as a function of the transmittance through the tissue and reflectance of the tissue. So transmittance from boundary 0 to boundary 1, reflectance from boundary 1 to boundary 0. So that's the kind of total sum. So you have this being contributions from your source coming from this side, and anything that's diffusely reflecting from the opposite side. Likewise, for your reflectance, again, it's contributions from these two parts. Typically, if we only have a single source in this direction, you can knock this down, so you can actually get, as a function of your original source, your transmittance and reflectance as based on the radiance that is exiting on either side of the boundary. And again, described by that simple first order differential solution that we have shown before. So what makes this kind of simplified solution kind of interesting is the fact that also, why is it called adding doubling? Is the fact that now you can go through and say, if I can come up with a solution for an arbitrary slab dimension, I can then add more slabs and propagate that solution all the way through, because at every single boundary you can determine what the radiance is in the forward and backward direction. So by adding, you can actually build it up. Or that's the doubling part, excuse me. I always get them mixed up. So you can just say, it's the same material, arbitrary thickness, it can be the sum of these solutions for multiple slabs of the same material. So it's very powerful in that way, because now you can have a scalable solution as a function of the thickness of your slab. But also, the adding part is the fact that now you can have a solution for this. You can also add materials of different optical properties and propagate that through. And so you can have material of different sides. So from a practical standpoint, back to when this was first applied in biomedical imaging techniques, is the fact that people would have liquid samples. You can put it in a cuvette, but how would you know what the optical properties of your sample was versus the size of the cuvette? So typically, this is a cuvette geometry, where if you know what the index of refraction of your cuvette is and the slide thickness of your cuvette, you can now go through and model the behavior of these two components and isolate the solution for the material you're interested in. So that's kind of a nice technique for the fact that it's an exact solution, it's scalable, and can account for these practical experimental conditions where you can't just have liquid stand on its own as a slab and hope to get an answer from that. So how is this a powerful model? So again, exact solution. There are no restrictions on scattering and isotropy, but these models will assume the Haney-Greenstein phase function. You can account for internal reflections at boundaries. So again, if you have index mismatches between, say, your glass and your liquid sample, you can calculate the Fresnel reflections based on the difference of index of refraction and account for that. But you have to also give something up. So something this simple and easy, there's always a consequence to it. So what are you giving up? There's no time dependence. The layers must be uniform. So again, finite in thickness, and the idealized measurement, it's infinite in lateral extent. So again, idealized solution. And this absorption and scattering must be evenly distributed within the volumes of these layers. So again, you still are required to have something that's completely homogeneous when you're making your measurement. And the illumination must be uniform. It can be collimated or diffuse, but it has to be uniform because again, we're simplifying down to one dimension. So when we are illuminating the sample, it has to have an even distribution so that at any particular lateral location, it's the same as its adjacent point. So adding doubling is a forward model that can describe the total reflectance and transmittance at the boundary of the layer. So again, this is not good for internal volumes. This does not really effectively describe fluence, but rather the radiance. And again, the model simplifies radiance into a one-dimensional function, assuming lateral homogeneity, and integrating over all the scattered angles. So the simplified model reduces the number of input parameters to only 5. So again, talking about the ill-posedness of the problem, having 5 input parameters is not as daunting as it could be. So the nice thing about having these 5 parameters is the fact that we can further reduce it by either independently assuming or measuring the values of index and anisotropy. And you can actually physically measure the thickness of the slab D. So if you take care of those 3 parameters, now you have a case where you have a measurement of reflectance and transmittance, so 2 measurements, and 2 unknowns, your absorption and your reduced scattering. So this basically reduces this ill-posedness issue that you typically will encounter. So if adding doubling by assuming index, anisotropy, and thickness, you can describe it in terms of absorption and scattering, and the outputs are your reflectance and transmittance. You can have now your inverse solution where if you have the inverse of this model with these assumptions, you can input your reflectance and transmittance and get out your absorption and scattering. So now let's go into the inverse model because there's also a number of other things that we can try to do to reduce the dimensionality. So, you can have things to reduce 3 parameters into 2. So again, you've already been introduced to the albedo. So again, looking at something where it's a unitless measure where you have the ratio between scattering and the total attenuation. and tau, which again, this is referring to an optical thickness, where you have your physical thickness augmented by the absorption and scattering you would encounter in tissue. So from measurements, you can now go through and say that your reflectance is equivalent to the radiance that you would measure in the backwards direction, and the transmittance is related to the radiance you'd measure through the sample itself. And as I mentioned before, index of refraction can also manage the surface reflections at boundaries. So again, if you have Fresnel reflections, not all the light that is at the boundary will actually enter the sample itself, so you have a further reduction there that you need to account for. And you have Haney-Greenstein phase function to describe the anisotropy. But the goal now is to find a solution where you have the absorption being some function of your measured reflectance and transmittance. Same thing for scattering. And again, this now involves an iterative strategy. And I believe that's also going to be spoken in more detail in one of the later lectures on iterative methods to minimize solutions of inverse models. So, just in very general terms, the setup of this inverse model, since it's an iterative process, start off with an initial guess at optical properties, calculate what the reflectance and transmittance should be from this forward model, and compare that to your measured data, and then test for goodness of fit. So again, then you go through, update your initial guess, try to minimize until you come up with a solution. So when we're looking at this inverse adding doubling approach, so what we can start to see is, over what range of optical properties can you get a unique solution? So if you start to look at a kind of mesh, ideally you want to have something as rectangular as possible, because in terms of your measurement sensitivity, any small amount of noise, you want to have some idea of what that measurement error may result in terms of your determination of optical properties. So under idealized cases, so again, total reflectance and total transmission, it's a relative value. It goes from 0 to 1. And what we can kind of see is from this solution grid is the fact that when you have very low transmission or low reflectance, this mesh kind of collapses. And so there your sensitivity to measurement error can have a huge impact on the accuracy of the optical properties that you reflect. So yeah, in this case, a small change in reflectance and transmittance could result in a large difference in the properties you're trying to extract. So another strategy to try to address this is to use something called the similarity theory. And all that does is change now our albedo and optical thickness values to these other units. And the result here is, by using these reduced parameters, you actually have the benefit of spreading out this mesh. So now you can actually parameterize these results with greater accuracy and less sensitivity to measurement noise. So that's basically setting everything up and saying, okay, we have this technique. I haven't gone into great detail describing it, but it's a thing that you can use to calculate absorption and scattering as a function of reflectance and transmittance. But now we need to go one step further and say, well, what do I actually mean when I say measure the total reflectance and transmittance? So now we're getting into how do you actually physically make a measurement of a one-dimensional model in a three-dimensional world. So in the 1D model, we integrated all the angular components into a singular dimension. But how would we capture and detect overall angles in a physical measurement? So that's where this thing called an integrating sphere shows up. So no surprise, integrating sphere literally means it's a physical integration of all angles. And so what this device is literally a sphere that's coated with either spectralon or magnesium oxide, some very non-absorptive, highly scattering material around the edges, such that any light entering the system at any angle is going to be collected and physically integrated over the dimensions of the sphere. And then you can go through and put a detector at one point, sample that, and you would now have a measure of all the light integrated over all angles. So in this geometry, if your sample is up in front, you have a light source shining a collimated beam in. Any light scattered over any of these angles get integrated. That's your measurement of your total transmittance. Likewise, if you have your sample at the back end of the sphere, shine your light in, any of the reflectance scattered over any angles will then be integrated and collected, and so that's your total reflectance. So yeah, I just described all that in words. Here it is again. But the key part is to think about this a little bit more, because the integrating sphere is a physical device. It's not perfect. And reflectance and transmittance are relative measurements. So these physical measurements can contain noise, they can contain bias, and again, the physical samples we're dealing with are finite in dimension. They're not some laterally infinite, idealized slab of tissue. So when we look at these spheres, we need to go through and try to understand where these different sources of error and bias can come in. And so one thing to keep in mind is they're not necessarily a 100% reflective. So when you actually look at a sphere, there's going to be some bias when you go through and take your transmittance and measurements, reflectance to the actual true values. There's going to be some deviation either in the positive overestimation or underestimation as a function of the actual reflectance values that you measure. Also, not all the angles are integrated. Again, you need to have physical holes to let light in for either the transmittance and or the reflectance measurements. You have to also have a sensor in there somewhere to actually make the measurements of the integrated light itself. But the best part is that people have already looked at this, done all the calculations, which are painful and tedious, but they've solved this for you. So again, accounting for the fact that it's not a full 4 pi, you have certain angles that are being subtended for the holes that exist, and that while reflectivity is not perfect, they went through, they've calculated this. So again, it's good to be aware of it and make sure you include it, but at least you don't have to derive it from first principles. So the other part is now calibration. So since reflectance and transmittance are relative quantities, they are dependent on your source itself. So typically for these types of measurements, what you want to do first is measure an empty sphere. So literally this is the integrating sphere without any sample in it. If you shine light directly in, you can kind of think of it as that's your 100% transmittance. And so that gives you your top relative amount. And then also, if you go through with your light source on and remove the back port, you can also make measures of any stray light that might be in your system, any dark noise of your sensor, and that would be your calibration for your 0% or dark measurement. So that gives you a physical measure of what 0% reflectance and transmittance should look like and what 100% should look like. So the other nice thing is that when it comes to taking your measurement data and actually calculating the optical properties is the fact that somebody else already has set up code to do that for you. So you don't need to consider and try to redevelop this from first principles. So there's inverse adding doubling code freely available on the web. This is the effort that was put forth by Scott Prahl And the nice thing about this code is that he's come up with a system that will actually do a lot of the practical accounting for the physical limitations of using this inverse adding doubling model. So again, he accounts for different imperfections, such as the integrating sphere properties. So you can input what the properties are. His code will then go through, do the sphere reflectivity, account for all the subtended angles that don't appear. It will also account for sample geometry and specular reflections. So again, knowing what the index is, if you have a liquid sample in a cuvette or not, you can input that. It will do the adding portion of the calculations for you. And the biggest part is it will account for side light losses. So again, when we're doing these types of measurements, we assume that we are capturing all the light on both boundaries. But since we have a physical sphere with physical dimensions, there is the possibility that when you shine light through your sample, it scatters around and does not either go into the sphere this way or into the sphere this way, but maybe propagate laterally along and are not accounted for. And so what his code does is actually goes through and say, if this is the physical dimension of your sample, and this is the physical dimensions of your sphere, I can use adding doubling to say, if I assume absorption and scattering of this, I would lose this many photons that would never get measured, and then iterate and redo it again to go through and minimize for that. So very nice. A lot of time and effort has been put into this code to account for all these things, so you don't have to. But it's a very powerful tool to have available. So when you think about your tissue sample, so other things that the inverse adding doubling code does not account for is surface roughness. So again, we're talking about a one-dimensional assumption. So we assume that when light hits the tissue is perpendicular, it's smooth, you won't get any specular surface roughness reflectance off of it. So again, that's just a part of the boundary conditions, and that is only described by Fresnel reflections. It doesn't account for tissue heterogeneity. So again, uniformity and lateral extent. The question becomes, well, how big do you have to be before you can safely assume it's infinite in lateral extent? And thickness variance in tissue. So again, it assumes slab, that it's a perfectly parallel, that you're not measuring one part of your sample is slightly thinner than the other. So errors in the variance in the thickness will propagate directly through with errors in your optical properties. So important take-home messages from this is, again, you need to understand the practical constraints and limitations of the model to best exploit the advantages of this approach, that this approach has to offer. So in terms of inverse adding doubling, rule number one is what you want to do is minimize sample non-idealities. So again, think about the sample thickness. The thinner the sample could help minimize light loss, but also if it's too thin, you're going to get something where your transmittance is a very high transmittance because it's so thin that most of the light will just go through unscattered, and your reflectance will be very weak. And so you have to have that balance between, okay, can I actually physically make the measurements? Do I have the dynamic range to capture all this? Versus minimizing side light losses. And sample preparation. So again, how do you prepare your sample to best mimic a slab of infinite lateral extent? So again, making sure there's no surface roughness. So if it's actually like ex vivo tissue, placing it between microscope slides will help keep it smooth and flat so long as there's no air bubbles in between, maintaining an even thickness, and minimizing any spatial heterogeneity in the illumination area. So again, if you have something that is heterogeneous, you want to use a smaller beam diameter to only sample one area at a time, but again, that's always tricky. So rule number two now goes and looks at your instrument itself. So again, the stability and configurability of your instrument. So integrating spheres in general are very easy to set up, but they're very lossy. You're only sampling a very small part of the total integrated light. So you can have very, very weak signals. So you have to consider, do you have a sensor that can either integrate long enough to capture the dynamic range? Also, you have different configurations where you can have a single sphere setup. And this would involve moving your sample from one physical location to another and making serial measurements. So in this case, they're easier to set up and easier to calibrate, but it's heavily dependent on how well you can collimate your light source, because your physical measurement of transmittance and reflectance are at two different locations. So if there's any issue with the collimation of the beam, you're looking at different parts, you're going to have an error. So another option that people have used are actually having two spheres at once. So you can actually put your sample in between. You make your measurements, transmittance and reflectance at the same time. The calibration is a little bit more tricky, but it will actually allow a little bit more slack in collimation, because you're now measuring your sample at one spot of the beam only. And again, they tend to be a little bit more expensive because you have to double up on all your equipment. You have two spheres versus one. But yeah, so using things like a variable iris is going to be means to adjust the amount of light in your measurements, but also changing your spot size will allow you to say, if you have something that is heterogeneous, you can actually have a smaller area, you illuminate the tissue at the consequence of the number of photons. But again, doing this, you want to have some ability to adapt with a single instrument rather than having to rebuild every single time. So the third rule is to have an expectation of the optical properties you hope to measure. So knowing something in advance of what range of optical properties will help you prepare your instrument, optimize the thickness of your sample versus the sensitivity of your instrument around that idealized range of optical properties. So, you can validate your results with known references or tissue simulating phantoms to go through and say, oh, if I have some unknown sample of optical properties, have a series of samples where you know the answer is, and make sure that they fall within that range. So again, you can do stuff with using cuvettes and having specific concentrations of dyes, microspheres to model the scattering effects. And again, a lot of the work in our lab here has been doing silicone phantoms where you can fabricate thin sheets, and those will remain stable over long periods of time. So again, it's something where you can come back a month, remeasure to make sure everything's all right, and check where the parameter space of where your reflectance and transmittance may fall. So again, going back to some of these reduced parameters, but the measurement space that you're looking at, to make sure that where in terms of the physical measurements of reflectance and transmittance you are, which you can gauge based on how thick your sample is, can put you in a space where you have a unique solution rather than having a sample that, say, in this case is too thin, that you could actually get crosstalk between absorption and scattering. So again, making sure that your parameter space is square within a closest to linear response between those two. So here's a list of references, and I think that was followed up as well in other things that we've used to kind of describe and set up this whole thing on inverse adding doubling. Yeah. So before I go into, just want to open it up to any questions people might have. And yeah. So.
I was just curious about the light that can hit the sample, hit back off the integrating sphere, then return to the sample. Mm-hmm. Does the calculations account for that, or how is that handled?
So in terms of the measurement, like the light source itself, or like what aspect of the light are you?
I guess I'm curious, like, it seems like if the light is transmitted through the sample, then hits off the integrating sphere and returns to the sample, then it would get
you get like
back.
multiple interactions. Yeah, so there is this iterative process that will account for it in the code that Scott Prohl provides.
Okay.
Under the idealized measurement, you have an integrating sphere. The sphere itself is also infinite in diameter, so it would only interact once. So the exact solution is under that condition, but you can go through, based on the reflectivity, the signal strength, estimate how many times it would actually hit. So yeah.
Okay, thank you.
So you mentioned that you can use dyes that can basically calibrate your system. Do you have any dyes that you'd recommend? And if some of these dyes are also like fluorescent, like you're using like methylene blue, like is that something that you kind of have to consider?
Right. So definitely you don't want to have anything that fluoresces because this model does not account for fluorescence. In the past, people have used things like India ink, which has a very flat absorption and can go over a pretty good range in both visible and near infrared. Challenges there are in liquid samples, you want to make sure you have deionized water because India ink can aggregate. So there is no longer a linear response, but yeah, I mean, those tend to be the standard ones that people go through: carbon black, India ink, just because it's flat and it's easy to control. But yeah, so, and you can always, just with the dyes, measure the linearity in a spectrophotometer first, so you can actually have an independent reference for that.
I see. And for Scott Prohl's code, like what wavelength range will it work for? I mean, is this typically for the visible and then your IR out to about like 900 nanometers?
Since it's an exact solution, it's independent of the actual wavelength range. So it's a calculation of just absorption and scattering as opposed, to light. So whatever wavelength you use, that's what it is.
I see.
So yeah, I mean, from a practical standpoint, anything from the visible to longer wavelengths will work with this technique. It's not limited to any like diffusion approximation that would say, okay, which range of optical properties. Typically you don't want to go into the UV because of fluorescence.
Yeah.
But yeah, so it's basically any wavelengths would work.
I see.
Yeah.
Okay, thanks.
So for the slab structure, I saw a similarity to the Bragg's mirror solution. So in the Bragg's mirror, where you need a high reflectivity mirror, it's kind of similar, and you have different refractive index slices. And only the difference is that there they are solving for Maxwell's equation, and here there's the RT solution. So do you think there's any kind of connection?
Yeah, I don't have I haven't really put any thought into that, so yeah, I really can't comment on that one.
Okay.
So for these codes that are available, do they only solve for mu A and mu S, or say you know one of the two and you're interested in solving for G? Is that a possibility with these codes?
Yeah, so there is some adaptability. So there are ways to actually use integrating spheres to actually solve for G. So there, rather than just solving for reflectance and transmittance, you can make a third measurement, which would be basically through a pinhole far away from the sphere. So you could actually get a measure of the unscattered light. And if you have a measure of unscattered light versus scattered light through the transmittance, you can estimate G. So there's three measurements, three unknowns. You can also constrain it to say if you know just either the absorption or scattering and want to know what the other is, you can make a single measurement just to calculate that as well. So yeah, there are, I think it's just the three different types of measurements that you can do that this code can be set up to run. So. All right. So I think, after that we can just go. We have until noon?
We have till noon.
Okay. Well, I won't take up all that time because it's...
We'll have more questions.
Yeah. So one of the the kind of examples that we've actually used this here is to actually characterize ex vivo tissue properties. And so there was a project going on looking at the properties of optical clearing materials to try to get deeper measurements into tissue. And then also, yeah, I've mentioned before that we've done a lot of work with these tissue simulating phantoms where we've actually constructed layers where we can actually stack on top of other layers of tissue and actually try to better recreate the kind of depth segmentation present in skin to see how other techniques would actually perform under different amounts of skin pigmentation. Can you really extract oxy and deoxyhemoglobin independently, even though you have this really strongly absorbing layer on top? So in terms of this optical clearing, again, this one group was interested in trying to map vascular networks in a mouse brain. And there were previous publications out there where people would take the brain of a mouse, slice it very thin, go through a microscope, try to map all the vasculature, and then reconstruct the full thing. But this required, slices that were like, 50 microns thick. And so that was just a lot of slices and very challenging to try to remap the whole network. So the idea with this project was, well, could we do a similar thing, but maybe only have 10 slices that are like 1 to 2 millimeters thick, clear the tissue, and try to measure it that way in depth. And the problem was there were a lot of different optical clearing methods out there, but nobody really knew how these things actually cleared the tissue. Was it something where they would actually, make the water or make the tissue, more hydrophilic, and that would actually fill up with water and reduce the index of refraction contrast between the different things? Would it actually change some of the chemical structure? Would it alter the dimensions of the tissue? So what we were doing in this, again, here's just one example, again, of the density of microvasculature you can see in cleared tissue. So again, this is using a dye before the rat dies to actually tag all the different vessels. So you can look at it under fluorescence, but when it's native and still uncleared, you have a very limited amount of vessels that you can actually identify due to the scattering of light. You only can really see the larger ones. You can't see the fine detail. However, once you start clearing the tissue, you can get higher and higher densities of mapping out these vessels in the brain. So, the question is, do we really understand at what point would be optimal for imaging? So how long do you have to soak the tissue in the clearing agent? How does the clearing agent actually reduce the scattering? Is it, a reduction in the number of the density of scatterers? Is it a change in the size of the scatterers? Some combination of both? Does it alter the morphology? So the idea is what we had as a student would actually prepare an optical cell. And again, we would actually have a fixed spacer in here, 2 optical windows, sandwich the brain in between so we can maintain the same thickness, and place it in the optical clearing liquid, and then just measure it over time. So again, just before, every hour, every couple of hour time points, and actually measure what is the change in absorption and scattering that we're seeing as a function of time when it's soaking in this optical clearing liquid. And again, our results here is that we initially assumed that this is ex vivo tissue. The amount of blood present is not going to change, so the absorption shouldn't change. However, the scattering should change, and that can kind of indicate the optical clearing potential. So the reduction in scattering would be correlated to how much does it clear and at what point in time. So there's this simple metric of the reduced scattering before and after the solution was added. So this is OCP is referring to optical clearing potential. And then what we could see is as a function of time, you see a general increase. And it's pretty much about the same spectrally over this range. And it just basically increases over and over again. So indicating that this is a change in the number density of the scattering present in the brain tissue. But again, just to go through and say temporally, how long do you soak it? When is it optimal? And there were also other different clearing agents to see what its behavior was, how well, which one cleared the most, so on and so forth. So again, we're talking about small, heterogeneous samples. So brain tissue from a mouse or a rat is not that big. So we had to have a small spot size and consider that. We would actually make multiple measurements in different areas and regions of the tissue just to capture any lateral heterogeneity. But this was able to go through and indicate the kind of dynamics over a period of a 24-hour period of optical clearing and how it would actually alter the scattering properties. Oops. Yeah.
So if you can go back to your previous slide. So do you have a notion, Rolf, of what the dynamic range of the baseline scattering was from roughly 400 to 1,000? Because these are all ratios.
Yeah, these are ratios.
Yeah. So
yeah.
Do you know what the original optical properties were?
Yeah, I'm trying to recall. It
Okay.
should be in the publication.
Okay.
But yeah, I mean, I think it's in that kind of 2 inverse millimeter scattering range that you would kind of expect, maybe even higher, because again, brain tissue.
Okay.
But
Okay. Thanks.
yeah. All right. And so the other application, and this is still a topic of ongoing work, is trying to validate layered models of tissue imaging. And again, that's something where standard inverse solutions, SDA models and all that, always assume homogeneous media. We know that skin is a very structured and layered tissue. And the wavelength of light that you actually shine will also have different depth penetrance into the tissue. So again, we just look at tissue as a 2-layered model where you have epidermis that contains any amount of melanin and the dermis underlying having the oxy-deoxy. How do we evaluate how robust our imaging techniques are in the presence of all this other potential source of variance? And again, there are several consequences of that, either misestimating the amount of melanin or distorting your spectral results of the oxy-deoxy. Classically, you tend to get things that in the presence of higher amounts of melanin, if you try to measure oxy and deoxy, you get lower oxygenation. You have an overestimate of deoxyhemoglobin. So the critical part is how do you really decouple something that is heterogeneous as a function of depth to truly isolate the parameters from each layer independently. And so there has been some different techniques that we've actually developed trying to use a layered model interpretation where, again, using estimates based on bulk optical properties as to how deep the light goes at every single wavelength, we can come up with a kind of partial volume effect model that would describe visible wavelengths. If they only go a couple hundred microns, if you separate the absorption from scattering, you can estimate what that depth is and calculate what is the concentration of oxy, deoxy, and melanin in that region versus near infrared, which will penetrate millimeters into tissue, calculate what it estimates the concentrations for oxy, deoxy, and melanin are, and then say, okay, our estimations are a function of the portion of tissue we actually looked at. So again, it might be only 5% of the total measurement in the near infrared that actually interacts with the epidermal layer, where in the visible it might be 50%. So you know you have a single concentration of melanin. You have two measurements that will give you two different results. You can actually scale everything to say, okay, if I have a layer thickness of this amount, then my interpretation of melanin concentration in one measurement and the other are the same. So yeah, we've actually modeled this approach to calculate, and from simulation can actually demonstrate that this approach is quite reasonable in reconstructing what is the actual concentration and layer thickness is. But that's in simulation. So the next step is to go through and say, can we come up with a layered construct where we know what those optical properties of each layer are, measure them, and see if we can decouple and segment that tissue correctly. And so that's where we've looked at these PDMS, these silicone phantoms, where we can put different dyes and different scattering agents in each one and lay them on top of each other. So we can fabricate, actually right now, we can go down to about 80 microns thick for the epidermal layer, use titanium oxide to approximate scattering in that layer. In this case, we were using naphthol green as the absorber. To actually approximate melanin right now, we actually use instant coffee. It's actually spectrally very close. So we can actually have something that actually approximates different amounts of melanin from that. And then what you can do is stack this on top of this layer, squeeze out all the air bubbles, you get tight optical contact, and then make measurements of this construct. And again, going in this range, we look at our stacked layered phantoms versus human skin. You can see this is from a high frequency ultrasound, the thicknesses of the epidermis versus dermis, and what we're able to fabricate in phantoms. So at least in depth, we can have something that's a close approximation, and then evaluate how well our imaging technique, So again, for our thin layers, we have this independent measure of what that optical property is using this technique, stack the layers on top of each other, and actually go through and determine what is our estimate using this simplified layered model for the actual concentration of each layer and layer thickness versus this independently verifiable standard. So yeah. So I guess just to try to wrap things up, I think the main question is when is inverse adding doubling an appropriate tool to use? So again, when it comes to methods and models to solve tissue optical properties, inverse adding doubling is just one approach. And so the key point is to really know what you are looking at to determine whether that's an appropriate tool or not. So again, going back to that main theme, if you understand when and or where each method best addresses the problem, will help you guide you to whether it's an appropriate technique, it has a chance to succeed or not. So to kind of wrap this all up, the strength of inverse adding doubling is that each of the steps of this model has a direct physical interpretation. It's just collecting the total reflectance, total transmittance, and using the results from those two sides to interpret what's happening in terms of scattering and absorption within this lab itself. Again, it can determine optical properties at any optical wavelength, at any scattering anisotropy, and it employs a steady state method, which as a consequence, you don't need to have an ultra-fast light source. You can just use a simple Heine laser if you want to do it at one wavelength. The system that we've been building here actually uses a broadband source and a spectrometer, so you can actually have a steady state broadband source, essentially just a light bulb. It can be simple as that, but again, there are limitations to that. So the weakness is the fact that it's a very slow and awkward method for calculating internal fluences. So again, it's geared toward measurements at the boundary, not what's really happening inside the volume of the tissue. And again, since it requires a simplification down to one dimension, it requires uniform illumination over discrete areas or volumes. And again, each layer must be homogeneous in depth and spatial extent. So if you're looking at thin slabs, want to get some answer or comparing it to something else, this is a nice independent tool to use. And that's where it's come into a lot of use here at BLI, since a lot of our instrumentation are wide field imaging techniques of semi-infinite materials or thick tissues, that you have a completely independent approach that uses a completely different model to actually go through and help validate whether we can believe the measurements of this. We can use this type of approach as a way to kind of give us a second point of reference to understand what is the variance that we're actually seeing. So in general classes, again, the next 2 days, you're going to be learning more about the reflectance-based methods. So other techniques, the spatial frequency technique, and temporal frequency techniques, spatially resolved. Each has their own measurement geometry and source, advantages and disadvantages of techniques, but it's something that you can keep in mind. Some of these approaches can be complementary, so you can use combinations of both. However, that would also add complexity to your measurement. Compounds limitations and constraints on tissues if you're using this. It's not always a one-to-one comparison using one instrument measurement versus another, but also has the opportunity of overcoming this big lurking issue of this ill-posedness that a single technique tends to carry. So I guess we can open up to any other questions. And yeah, I just wanted to also give you a preview of this afternoon's lab. So there's actually going to be 2 parts to this lab. It's going to be focused on inverse adding doubling. We have a kind of simulated data analysis part, just to go through, load pre-measured values for different tissue types and look through the sensitivity of it. So varying one parameter. What if you're slightly off in your estimation of anisotropy? How would that affect the data? What if you're slightly off in terms of thickness and stuff like that? So that's one part, is to go through that. But we also have a system, a single sphere system with a silicone phantom sample that you can actually physically go through the steps, make the measurement, run the actual Scott-Prahl processing code on that computer, just to get a feel for what does it physically take to do that. So, that's going to be going on at the same time, and hopefully we'll have enough time for everyone to kind of go and just run through the test measurement. But yeah, I felt that, it's probably better to actually get more of the physical measurement aspects and understanding on how that works, rather than just doing the simulated data and talking in more theoretical terms. So with that, any more questions?
Could you review or speak a little bit more to the zeroing of your system with the 100% and 0% measures? Because I believe we have a system in our lab that is a spectrophotometer, so it does this, but I've heard there's some intricacies in what you use as your, stand-in for those measurements.
Right. Yeah. So for the kind of calibration steps, the one thing is we'd have a closed sphere, so light can only enter in through the transmittance port. And you'll see this in the afternoon. What we actually have is a spectralon puck that we actually move to the back. So that's the kind of 99% reflector in that. And so making a measurement of that, that's kind of like the total amount, the 100% amount of light you can possibly get. And then what we do for our zero is actually close the shutter to the lamp, So that way, when you make your measurement, it's only the dark noise of your spectrometer and any stray light that might be in the system to characterize that. And we do that for every single measurement. So even if they say as a sample is in a certain location, it may block some of the stray light. We measure that every single time. And so for the zero, it's just a straight subtraction of your measurement minus your zero. So that shifts it. And then for your calibration, then it's the ratio of your 100%. So your measurement divided by your 100%, that becomes now your calibrated spectral data.
On your strength and weaknesses slide, you talked about how the method also works for internal fluence, but it's low and outward. I'm just wondering like, how the calibration work for that case.
So again, in terms of calculating internal fluence, the approach would be is that, since you can double every single time with the adding doubling method, basically the fluence, the internal part, why it's really slow and awkward is that you basically have to set up arbitrary boundaries at discrete points, calculate it, and then you can kind of calculate it all the way through. So that's where it's not a very effective way, but it is possible since you can just basically parse every subvolume from there. Yeah. You don't have to have questions, that's okay.
So Rolf, how often are measurements made on both, say, an inverse adding doubling, an integrating sphere system, and an SFDI system just to look at agreement or disagreement? And because they both have very different calibration procedures.
Right.
I mean, typically you can't use a piece of spectralon, or at least not very easily, as a reference standard for, say, an SFDI instrument.
Yeah, no, and I think it's because they are so different, that's what makes it kind of useful. Because if you can get agreement between those two systems, the likelihood of that happening by random chance is very low. So typically when we fabricate, different tissue simulating phantoms, particularly calibration phantoms for systems, we will use both. When we fabricate the phantom, we'll make a thick phantom to be measured on reflectance-based instruments, and then several thin samples at different thicknesses for the inverse adding doubling. So typically for any one phantom, we would have 3 different thicknesses. So again, that's an internal sanity check for inverse adding doubling to say if I measure it at 700 microns and at 1.2 microns and at 3 millimeters, that they should all overlap because it's the same material, you're only changing the thickness. And so that's an internal quality check to say, okay, we have 3 different samples, 3 different thicknesses. If they all line up, we're quite confident with that. And then we'll compare that absorption and scattering values to a SFDI instrument to see how well that would line up. And that's how we can kind of go through and have this kind of cross-platform validation.
So what are typical ranges of agreement between those two techniques?
It depends on who fabricates the phantoms. But yeah, I mean, we can usually get within 1 to 5% agreement in terms of absorption and scattering if I do it.